today I'll present a talk about a weak form of self-testing. My name is Jędrzej Kaniewski. I'm based at the University of Warsaw. And before I begin, let me thank the organizers for putting together such a wonderful event. I guess we had to wait for it for quite a while, but it was totally worth it. So the outline of my talk is as follows. I will start with a brief description of Bell non-locality, and then I'm going to tell you a little bit about the usual self-testing and based on the CHSH example. And then I'll proceed to discuss the weak self-testing, which is the new results. And then I will just briefly tell you about certifying randomness using this, this new method. And finally, there will be some conclusions and open questions. I will try to keep an eye on the Discord. So if you have any questions during the talk, please, just type it up. Okay, so Bell non-locality. So we already saw this in the previous talks. I guess here I'm really just interested in the simplest Bell scenario, just two boxes, inputs XY and outputs AB. And, we are in the fully device independent setting. So we kind of assume that the only thing that we have access to are the statistics, which I denote by PAB of XY. And, for the purpose of this talk, I assume that the statistics you see, they are quantum. Okay, so there exists a quantum state and some measurements, which I denote FAX for Alice and GBY for Bob, which give rise to exactly these statistics. Let me just remind you that we say that a probability point is local if it admits a decomposition of this form, where lambda is the so-called local hidden variable, and then PA and PB are some local response functions of Alice and Bob respectively. And essentially, the great discovery of Bell was just to show that the set L, which is the local set, is strictly smaller than the quantum set, okay? Or in other words, that quantum mechanics is Bell non-local. So now, of course, there is a natural question. If you're given a point, which is quantum, how do you show that this point is not actually a local point? So how do you show that there is really something non-classical going on in your devices? And one of the most natural tools are the so-called Bell inequalities. And for the purpose of this talk, I will just think of them as, some kind of linear functionals. So if you're given a sequence of coefficients, which here I denote by a real vector C, you can define this inner product between these coefficients and your statistics. And then you can just, find the maximum over the local set. That's what I defined by beta L. And you can also look at the maximum over the quantum set, which I denote by beta Q. And I will also assume that these two numbers are different, so that the beta Q is strictly more than beta L. And of course, if the statistics you see give you more than beta L, this is clearly an indication that your point does not belong to the local set. I mean, this is really just the hyperplane separation theorem. So there is an interesting observation about non-locality, which is that if your state is separable, then it will always give you local statistics, okay? Whatever measurements you do in it, you will always get local statistics. And this is just because if you're given a separable decomposition of a state and you perform some measurements on it, you can essentially just write down a local hidden variable model. So this tells you that non-locality, if you see a non-local distribution, your state must be entangled, okay? So this is a nice quantitative connection, qualitative, but how do you make it more specific? How do you make it quantitative? Okay, and one way of doing it is self-testing. So the usual strong self-testing based on a Bell functional, it kind of works like this. So for a Bell functional, which is this vector of real coefficients, you can define a Bell operator. Okay, so this is what it is, and it's easy to show that the value of the functional on some probability point is simply the trace of the Bell operator with the state. Okay, this is just some simple algebra manipulating symbols. And essentially, if you want to prove that the quantum value is upper bounded by some number, it's equivalent to showing that the spectrum of the Bell operator is always upper bounded by some constant, okay, which I here write as W less than C times identity. And this has to be true for all measurement choices. Okay, so this is the first remark. And the second remark is for the purpose of this talk, we only care about measurements with two outcomes, and measurements with two outcomes have a nice way of, there's a nice description in which, instead of talking about two separate operators that add up to identity, you can just talk about observables, which are defined as the difference between these two operators. And then, this mapping is one-to-one. So kind of if you characterize one, you have the other one, and vice versa. So for the purpose of this talk, we will always talk about these binary observables. So the CHSH operator, as probably all of you know, it reads like this, where the AJ are the observables of Alice and the BK are the observables of Bob. And it is well known that the local value of the CHSH operator is 2, while the quantum value is 2 root 2. And it's also known that the maximum violation can be achieved in a essentially unique manner. Okay, this has been proven in many papers a long time ago. Here, I don't really want to go through the proof, but I just want to tell you that the proof is based on finding a sum of square decomposition. Okay, sum of squares decomposition is something that kind of comes from the NPA hierarchy that Stefano was talking about, and it essentially boils down to finding a neat way of writing your Bell operator. Okay, so for the purpose of CHSH, you define two operators like this, V0 and V1, which are just functions of the local observables. And then you realize that W can be expressed in this form, where on the right-hand side, you have squares of the observables, which we know are at most identity. And you also have some terms like V dagger V, which are positive. Okay, so essentially, if you can write your operator like this, you can immediately see that the eigenvalue cannot exceed 2 root 2. So this is a proof that the CHSH value cannot exceed 2 root 2, but it actually turns out to be tight because you can find the realization where this is saturate. And so in the first step, you find what the maximum value is, but then by analyzing the sum of square decomposition, you can actually characterize the quantum realizations that achieve the maximum value. Okay, and the first thing you realize is that the measurements must be projective on the local supports if you want to achieve the maximum value. And then you also deduce that the observables of Alice and Bob, they have to satisfy certain relations. Okay, so this is one of these relations, and you kind of see that, okay, well, A0 acting on the state must be the same as certain linear combination of B0 and B1 acting on the state. But because A0 squares to identity, so should the linear combination on the right-hand side, okay? And if you simplify this, you realize that B0 and B1, the two observables of Bob, must anti-commute. And once you realize that they anti-commute, you can actually write down exactly what they look like. Up to unitaries, they are essentially just sigma x and sigma z, potentially tensored with some identity on a larger space. By symmetry, A0 and A1 have the same form. And once you have the explicit forms, you can write down the Bell operator, and you can determine the eigenspace corresponding to the maximum eigenvalue, 2 root 2, because this is essentially a 2-qubit operator. And then you can write down an explicit form of the state and the observables. Okay, so this is what we call a rigidity statement. If you see the maximum violation, the observables look like this, and the state looks like this. Okay, essentially, you can see that what's happening is that there is a maximally entangled state of 2 qubits on which you do certain well-defined measurements. And of course, there can be some auxiliary state that you essentially ignore because all the measurements act trivially on it. But of course, you have to allow for it. So this is the standard rigidity statement for CHSH. And so let me just briefly recap. So what is the strategy that we used here? So first, we find a tight sum of squares decomposition. Then you use it to deduce algebraic relations between local observables. Then you deduce their exact form up to unitaries and extra degrees of freedom. And finally, you construct the Bell operator and find eigenspace corresponding to the maximum quantum value. So this is a nice method. And essentially, what we do in this work is we apply it to a slightly more complicated family of Bell functionals. Okay, so one thing that is quite interesting, and it's kind of clear when you think about it, is that if you have a Bell functional which has the self-testing property, it immediately implies that the maximum violation is achieved by a unique probability point. Okay, so in this plot, you have the local set, you have the quantum set, and basically for a self-testing Bell inequality, we have this feature that the quantum value is achieved at a unique point. So then you ask, okay, so what about Bell functionals that do not have a unique maximizer? And this was essentially the starting point of this work. So there, geometrically, the picture looks more like this, okay? So the quantum value is achieved by several points. And we actually had an explicit example already when we started. This is the correlation part of the infamous I3322 function, okay? So we know that the local value is 4 and the quantum value is 5, but the maximum violation is achieved by multiple probability points. So once you realize that there's no unique maximizer, you deduce that there's no rigidity statement of the usual kind. But of course, the question is, can we still have some weak form of self-testing? And the answer turns out to be yes. So already in the previous paper, we have given a tight sum of squares decomposition for this functional. It looks like this. It is a bit more complicated than the CHSH sum of squares, but in fact, it's not so different. It has one more term, but otherwise, again, these are simple combinations of the various observables. And again, now we try to deduce something from observing the maximum violation. So we immediately deduce that the observables must square to identity on the supports, okay? So the measurements must be projective. That's great. Okay, and now what can we deduce about the relations between the observables of Alice and the observables of Bob? And here, with a little bit of algebra, we can deduce certain algebraic relations. So for instance, for Alice's observables, we can deduce that if I take the difference between A0 and A1 and I square it, I should get identity. Okay, this can be shown to imply, again, a very specific form of A0 and A1. Essentially, up to a choice of basis, they correspond to a certain pair of binary observables on a qubit tensor of identity. Okay, so again, we can show that the angle between A0 and A1 is somehow well defined. And then if we combine the other terms from the sum of square decomposition, we can get some more algebraic relations. And in fact, if we now combine the previous characterization of A0 and A1 with the new algebraic relation, we can say something about A2. And essentially, A2 has to be orthogonal to the A0 plus A1, okay? And because we chose A0 plus A1 to be proportional to X, so A2 has to be in the YZ plane, okay? It doesn't tell us exactly where in the YZ plane it should be, but it has to be in that plane. So if you think about this geometric, if you think about the geometric interpretation of this, you can, oh, did I skip the geometric interpretation? Oh, okay, sorry, I had a picture here, but maybe it comes later. Okay. This characterizes the measurements of Alice. We have the same characterization for the measurements of Bob because the inequality is symmetric. Okay, so again, kind of like in the previous case, we know something about the local observables. So now we can construct the Bell operator. Okay, now the Bell operator is a bit more complicated because there is not just a single choice of observables, but there is kind of like a one parameter family for Alice and one parameter family for Bob. So that's why now I have these EJ vectors, which is you can think that it's kind of a classical register that Alice holds that tells her what angle she chose for the third observables, and there is also the FK which tells Bob what angle he chose for the third observable. Okay, and now the R is a 2-qubit operator, but it depends on these two angles, which I denote by U and V. Luckily, this is still a 2-qubit operator, so we can actually diagonalize it explicitly, and we can show that the largest eigenvalue equals 5 if and only if the angles of Alice, the angle of Alice and the angle of Bob are the same. So now if we choose a smart parametrization of these observables, you actually can show that the corresponding eigenvector is always the standard maximally entangled state. So you can now write a self-testing statement for the state, which is basically of the same form as before. Okay, you have the maximally entangled state on some 2-qubit registers, but on top of that, you have this auxiliary state sigma, which is shared between Alice and Bob, and it essentially acts as a classical register, which allows them to coordinate what angles they use for the last observable. Okay, and they always have to use the same angle, because otherwise they are not able to achieve the violation, the maximum violation. So the conclusion is, we have a Bell inequality for which every optimal strategy is just a convex combination of some family of optimal 2-qubit strategies. Okay, and these 2-qubit strategies are parameterized by an angle from 0 to 2 pi. And if you think about what happens in the space of correlations, in fact, what happens is that at u equals 0, you have a point which is on the face of the quantum set, but it's an extremal point. And as you increase u, you go to the middle of this phase. For u equals pi, you hit the other end of the phase. And then if you increase u even further, you start going back. And what is kind of interesting is that these two, so the u equals pi over 2 and u equals 3 pi over 2, they are related by complex conjugation. So these quantum realizations are almost the same. Okay, they are related by complex conjugation, so you don't see a difference in the statistics. So as a side product, we also have shown that the set of optimizers of this Bell functional is just a line. Okay, so for many Bell inequalities, it's just a single point. Here, it's a bit more. It's a line, so it's a one-dimensional region. And it's also worth saying that the endpoints are actually self-tests in the strong sense. So if somebody tells me that not just I maximally violate, but also I maximally violate and I'm at the end of the line, then I can actually write down the usual self-testing state. But if somebody tells me only about that I'm on the line, then I don't really know. Okay, and the last thing I want to mention is about certifying randomness using this Bell function. Okay, so this is like a setup that you can use in some quantum cryptography scenario. So suppose that Alice and Bob observe a Bell violation, and Eve is trying to guess the outcome of Alice for a specific setting. Okay, so this is kind of basically the quantum random number generation setup. So let us start with A2. So luckily, this is a problem you can study numerically. Okay, and this is a plot. So on the x-axis, you have the observed violation, and on the y-axis, you have the guessing probability. So the probability that Eve correctly guesses A2. As we expect, if you see the maximum violation, Eve's guessing is 1/2. Okay, so she has no idea what the answer will be. But when the violation is 4.5, okay, Eve can already guess. Okay, so this is not great because the local value is 4. Okay, so if you see 4.5, this is still significantly above the local value, but you have no security. Okay, so it's clear that the A2 is not so good at generating randomness. Luckily, the other two observables, so A0 and A1, they're actually much better. So if you make a similar calculation here, you get a plot where, again, for the maximum violation, you get maximal randomness. That's great. And then there is some randomness, even if you're very close to the local set. Okay, so essentially, as soon as you see a violation, you have some randomness in your output. And basically, this is qualitatively the same situation as in the CHSH case, so in the kind of strong self-testing case. And let me finish up with some conclusions. So in this work, we have shown that there is a new weak form of self-testing, where the maximum violation certifies the state, but doesn't fully characterize the measurements. Okay, it characterizes the measurements to some extent, but not as strong as usual. Moreover, the state certification is robust to noise. Okay, and this was to show this, it required a new construction of extraction channels, which depend on 3 observables instead of the usual 2. So this was like a new component that we had to add. Nevertheless, the randomness certification power of this is qualitatively analogous to that of CHSH. So that's nice. And in fact, in the paper, we show an entire family of such correlation Bell functionals which exhibit the same behavior. Okay, so it's not like a single example, it's actually a 1-parameter family of examples. And as open questions, I would just like to mention 2 things. So in here, even though we don't have the full rigidity, we still have, at least from the randomness point of view, it behaves similar to the CHSH. I would be very interested to know if there are examples where the lack of rigidity really breaks something in your cryptographic protocol, for instance. And the other thing that I would like to, I'm interested in, is whether you can find a bipartite Bell inequality where the maximum violation can be achieved by distinct states. Okay, this exists for 3 parties, but somehow we know that 3 parties are more complicated. There are many entanglement classes and so on. But for 2 parties, this is not known, and this would also be very interesting. And finally, I would also like to bring to your attention a related independent work by Gebaratina et al., where they show a similar weak self-testing flavored results, but their results are based on lifting. So it's a bit different. Okay, so with this, thank you very much for your attention. And okay, and I see that there are 2 questions on Discord. So should I read them, or Matthias, are you gonna read them to me?
It's my job to read them.
Oh, sorry.
Thank you very much. Yes, so there's already 2 questions. So the first one is about this positive polynomials. So they're counterexamples to the sum of squares, which was once, I guess, the 17th problem, and whether there's any relation.
Okay, so I must admit, when I saw this comment appearing during my talk, I thought this was a joke from Jarek. Okay, but are there? So okay, so this one I honestly I don't know. I mean, we know that, okay, so these sum of square decompositions, one way of finding them is through the NPA hierarchy, okay? And the NPA hierarchy is known to converge. So I guess if you look at sufficiently high level, you should be able to find a tight sum of squares decomposition. So that's what I know. I don't know how it's related to this more abstract formulation of the problem.
Yeah, okay. Zinpeng wants to know, how did you find out about this special inequality in intuition, how to construct it? Okay, so this is a question I can actually answer. So basically, in some previous work, we're looking for functionals where the maximizers are not unique. Okay, and in fact, we basically just looked at some examples from literature. And we kind of just noticed that, one of us optimized and got one solution and somebody else optimized and got a different solution while still having the same Bell value. So then you realize, oh, okay, so, there are these inequalities where the maximizer, so the maximum value is achieved by many different probability points. And then we kind of noticed that even though the quantum realizations are, of course, different, they still belong to a certain family. They satisfy some relations, okay? And so basically, it was really just a matter of looking at these correlation functionals a bit more, finding these sum of squares, analyzing these sum of squares, and after that, it was actually okay. So kind of this is how we got to this example, and we managed to analyze. Mm-hmm. So I have also a question, did you somehow look for nonlinear inequalities? I mean, because, if you have this kind of degeneracy, it would be natural either to take 2 witnesses or to just look for nonlinear thing. Do you have any idea that it would be useful to do that? Okay, so look, so we did not look at nonlinear things because you know, it feels that this sum of squares method is really tailored to linear things. So I wouldn't even know how to study the nonlinear variant of this problem. But you're right that I mean, one way of like, so if you have as I mentioned, if you have this line segment, and if I just tell you that you're somewhere on the line, you cannot make a full self-testing statement. But if I tell you you're on the line, and moreover you are, you know, extreme on the line, then you actually go back to the usual strong self-testing scenario. So I would say I wouldn't know how to use nonlinear inequalities to study this. But for instance, if you tell me that there is a couple of linear uh, inequalities that you're saturating at the same time, this can actually, you know, define your point sufficiently well that you can actually make stronger conclusions. So, and I think this is something you can still attack through the sum of squares technique.